Okay. So I'm talking about this new project called Runway that I've been working on. I just released it last week. It's open source. You can go try it out probably after this talk at runway.systems. And yeah, it's a new tool for distributed and concurrent system design. So in my talk, I'll first go over why I think we need new tools for distributed systems design. And it's not just distributed systems, that's just where I'm coming from. That's what I'm interested in. Part 2, I'll talk about the Runway tool itself and go into a few demos of models I've built already. And part 3, I'll talk about how you go about building your own Runway model. We're a pretty small audience, so feel free to just interrupt if you have questions. So, distributed systems are hard. They're hard to understand. They're hard to communicate about. Probably not too many people here would disagree with me, but just to be clear, you're running a piece of software across the network, so you've got concurrency while different servers are executing the same thing. That's hard to reason about. You've got message delays, so by the time you receive information, it's potentially already stale. You have to deal with failures, and it's not like you could just have a try-catch block. You have to deal with failures during failures, cascading failures. And this leads to just many possible interleavings of events. It's hard for humans to reason about. And then in a running system, because it's across a network, we have little visibility into it. We tend to have poor debugging environments. It's hard to get a global view of everything that's going on so that you can really understand it. I'm not really talking about Raft in this talk, but that was my previous project, and I'm going to use it in a lot of examples. So a little bit of background. Raft is a fault-tolerant consensus algorithm. That's the logo. I do have stickers. And it's used in a whole bunch of systems, distributed systems these days. But it's relevant here because I've struggled as a student trying to find tools to help with validating the design, making sure that it was going to behave as it should in all situations. Quick summary of Raft. It's kind of 2 parts. The first part's leader election, where the cluster uses a majority voting algorithm to elect a leader. And the second part, that leader just replicates its log to the other servers. Those are called followers. So here's an example of a difficult bug in Raft and why this stuff can be hard to think about. So in this example, server 1 was leader, it partially replicated an entry and it crashed. Server 5 over here became leader, created an entry and crashed. Server 1 became leader again, continued replicating that old entry, and here a previous version of Raft would have marked that committed. That was incorrect because actually if it crashed yet again, server 5 could become leader and overwrite that entry. So we're not just having to think about one failure. Here it was this bouncing back and forth, this crazy interleavings of events. It's quite difficult to reason about. We could use some tools to help out. Okay, so on the left, I've listed stuff that we as an industry kind of do today if we're worried about correctness of our code. Code reviews, forms of testing, benchmarks, etc. And the problem is these are only really good for finding implementation errors. An implementation error being one where I had the right idea in my head, I typed it into my editor, and it just came out wrong. And so we find that in testing, and then we can correct that pretty easily because it's localized. But if you're finding design errors this way, it's simply too late, right? An error in design might take a complete rewrite to fix, or you might think you can just manipulate this one module, but you need to understand how it's going to impact the rest of the system. And because distributed systems tend to be expensive to develop, then these design errors can be very expensive. So hopefully it's not too controversial that we should be trying to find the right design sooner. Well, what should we be doing in our design phase? We should have, I think we should have two goals: communication and understanding. So communication, whether to yourself, to your team, to the whole world, how do you build intuition quickly? How do others build intuition about your design? Can you communicate unambiguously so that if there is a question, they can really understand what you meant to say? And evaluation. Is this the simplest design? That's the only way we're going to get it right. Does it seem to be, is it safe? Does it perform well? Is it available? Does it scale? Those are all questions that I think we should try to answer before we go write our production code. But what are the design tools that we actually use today? It's a bit washed out. A whiteboard, back of the envelope calculations, and a design doc. That's pretty much it. At least in industry, that's pretty much what people do. And those don't quite meet the goals up top, right? You're not really learning much about correctness, performance, availability. You're not communicating unambiguously in a design doc. Design docs are terrible. They're, maybe they have pseudocode, but they're very unclear. Okay, so I claim that's not enough. And then there's this other stuff over here that we could be doing, that some people in academia are doing, or occasionally in industry. Visualization, specification, model checking, simulation. These are things we'd like to do, things that aren't too difficult to do, but things we don't tend to do. So what do these have in common? Well, they all use system models. And I'm defining a model as a representation of a system that captures its essential components and omits irrelevant details. So here's a Raft visualization I did. In this half, it's all about leader election, where the important stuff is these timeouts. When is the server going to start an election? And these messages actually go and reset the timeouts, so it's important to see those. It's not important to talk about the network topology. The messages here might take a little longer, a little shorter, but we don't really care how many switches they're going through. We don't care about processing time at these machines, any of that. Here, log replication. Really all you want to know is what do the logs look like when you compare them with each other. That's the most important thing there. In specification, you want to omit irrelevant details so that someone can actually read your spec and understand it without getting into implementation details like the width of an integer or what logging library, what threading model, how you're encoding messages. None of that matters. For model checking, you need your model to be pretty small, otherwise the model checker is not going to complete. And for simulation, you don't necessarily need a small model here, but this is something that we want to do before we have the real code. So all of these are kind of similar. And in Runway, my goal was to combine them all into one tool and see how much one model, how much benefit you could really get from the same model. So this is part 2 on Runway itself. This is an overview of Runway's architecture. So you type in you give it a specification. Sometimes I'll refer to that as a model. And this specification is code, but it's not, it's not Java code. This is code that's interpreted by Runway, and it's very stylized. It's in a domain-specific language. So Runway can take that and run it through a randomized simulator. And this produces an execution. An execution, sometimes called a history or a schedule. This is, the series of events that's going to happen. Well, server 2 will receive a message. Then server 3 will process one. Then server 1 will send it. And that execution can get plugged into a visualization. So over here, for whatever state you have, you're going to have to describe how to display that on the screen. But Runway will give you the framework to produce the animation. You can then interact with that. So you're basically changing the execution, and you get that visually. The other thing you can do is, if you're generating long executions or you're generating many of them, then you can collect a whole bunch of data about how your design, how your model behaves, and from that you could graph it. And as I'll show you later, if you want to zoom in on a particular data point in your graph, then you can come back down to the visualization. Alternatively, if you're worried about safety properties, so you can take that model, plug it into a model checker. So this is going to brute force explore its way through the possible stakes that your model may enter, and you can define invariants like I never want more than 1 liter per term, and if the model checker ever finds an error, it gives that back to you as an execution, which you can then watch visually, which definitely beats digging through log files to understand what went wrong. So the whole idea here, none of these pieces are new, but the whole idea of Runway is that we're integrating all of this into one tool so that you can write one model and get many benefits. And the hope is we weren't really doing these things before, but if you can do them all easily together, maybe we'll start. Okay, so next I want to do a demo. I've actually got 3 different models: the too many bananas problem, the elevators, and Raft. So bananas. Malaga has an issue with its bananas. I don't know what's wrong here. This is a picture in the hotel room, or in the hotel lobby today. The bananas are all brown. It's not okay. I mean, I think we can do a better job at allocating bananas here. And so I want to teach you about the too many bananas problem. So let's see here. I'm going to load up runway.systems. This is 10 megabytes of JavaScript that just got pulled down into my browser. Awesome. And it's all running in my browser from here on out. The banana model actually just got pulled down from GitHub. So in the too many bananas problem, it goes something like this. I live in a house with a few roommates, and we all like bananas. And so, sometimes I get hungry, and I'll eat a banana, and then I'm happy again. Okay, and maybe my roommate will get hungry and eat a banana, and they'll be happy again. But now we're out of bananas. So the next person to get hungry has to go to the store, bring back some bananas. The model's just, you get a random number of bananas back. So this person got unlucky and just brought home 1 banana. So they bring it home, and then they eat it, and they're happy. The too many bananas problem, well, I'll run the randomized simulator, and you can watch it happen. I don't know when it'll happen, but it's basically, too many people go into the store, and we ended up with too many bananas. That's defined as more than 8 bananas is too many. You don't want too many bananas because then they'll go brown before you eat them, and that's wasteful, and you end up with the Malaga situation. So that was a little quick, but let me point out there's an error message up top. It's a little ugly, but it says we failed our invariant called banana limit. Bananas was supposed to be less than or equal to 8, and it's not. And let me show you how that happened by just backing up the timeline a little bit. Okay. Well, I guess it happened very early on, huh? So this person was going to the store, but before they got back, 2-3 other people already left for the store. We basically have no knowledge of what our roommates are doing. Now, fortunately, I have a correct version of this model. I figured out a solution to this. So now when you eat a banana, now when you're out of bananas and you go to the store, you're going to pin a little note to the front of your house there. It says, "Gone to store." And what this does is it's a notice to your other roommates, so they're no longer allowed to leave for the store. I can't make them do it because it's against the rules of the model. And so now I can run a randomized simulation, and we're just never going to end up with too many bananas. Bananas are not going to waste here. Okay. And we'll go through the too many banana code later. But let me... so those are abstract time units that I haven't put a label on. This is an asynchronous model, meaning that it just at every tick it takes a step, and I think by default it's like, I don't know that we've really gone through 4,500 steps. No, we've gone through 500 of them. So maybe it's every 10 of those we're taking a step. As I said, this is still pretty rough. Definitely looking for help on it. So here's the elevator model, and in this one this is an actual timeline, so it's approximately real time. So this is it's pretty close to my building in San Francisco, and the issue with our elevators is they take forever, and oftentimes they're just very poorly sent to the wrong floor. And I think this is a somewhat accurate model of those, though I don't really have the code for the real system. So there's 9 floors, there's 6 elevator shafts, and the number here, like that person is trying to go to floor 8. So they arrive, they get off, the Z means they're sleeping, and then they'll randomly wake up. So elevators are pretty interesting from a simulation point of view, because I kind of want to know, how do I speed up trips around my office, and so down here, well, if I scroll down, I get this is all the state of the elevators. So I have 5 people, some of them are sleeping, riding, or waiting for an elevator. Floor controls are those little buttons on the floor. I just named them that. I don't know if that's correct. And here are the elevators that can be in different states. But while this has been running, I've been generating this graph. Can you tell the difference between the colors in the back? So the bottom bars, they're supposed to be blue. That's the time that each bar represents one elevator ride, and so this is the time that this person spent waiting for an elevator, and then this is the time this person spent riding the elevator to get to their actual floor. So I can pause that and just continue generating the simulation in the background. This is using remember, we're just in my browser, so it's just using a web worker thread. And I'm starting to collect a whole bunch of data. Oh, and that's exciting. Got a really bad spike there. So I can just sort that, and we can clearly see, like, this person, whoever they were, they're not happy, right? They spent a really long time waiting for that elevator. So I can I can click on that bar, which moved my timeline over to when that ride started. And it's highlighting, you might not be able to tell, but it's highlighting the elevator, which is the second to last one, and the person right here who's eventually going to get on that elevator. And we can just watch to understand why did they have to wait so long. So they're on the 6th floor, they want to go to the 8th floor. Let's watch that elevator. So it's picking someone up. It's having to go all the way down. Drops them off, turns around. Oh, picks them up again because they woke up quickly. Picks more people up. Still waiting. Drops that person off. Yeah, that took a while. Like that, maybe that wasn't the best elevator to send at that moment. I don't know who programmed this model, but they're incompetent. Cool. And then the last one I want to show you, this is Raft. So it's very similar to Raft Scope, if you saw that, my earlier Raft visualization. This is important because it's actually it's showing a real distributed system. So here we're going through an election. Server 5 is going to time out, and it's requesting votes from everyone, and it's become leader, and now it's sending heartbeats. And I can interact with this. So I can click on this server and submit a request to it. Check out what's going to happen on the timeline. So we've got the worker thread is running a little bit ahead, generating a little bit ahead in the execution, and I'm changing the current state of the world. So I'm submitting a client request, and that basically forks my timeline. That client request and everything got committed in this execution. And I can actually go back to the original execution where that client request just doesn't exist, which is kind of cool. I can continue interacting with the model. So I just killed that server. We're hosting another election. It's looking like these two will time out. And neither one, we had what's called a split vote, so neither one became leader, and we're having to wait for another election here. Cool. So now server 2 is our leader. So let me restart that. I want to show you a really basic simulation on here. So I have in this model, I've got the state is the servers with their various internal states. The network, which is currently empty, but that holds any message that's being sent at the moment. Election history is just used for an invariant to make sure we've got no more than one leader per term. And I've got this magic one down here called reset stable leader. Let me just toggle that over to true. So now when I run the simulation, what's going to happen is, if it works, it's a little weird. The moment that we get a leader and everyone agrees on that leader, it's just going to reset the state and host another election. See that? So we were in term 2, we just reset back to term 1. And it should do that again. Okay, so maybe you can see where I'm going with this, but I'm starting to build up a graph of every election that's been happening here, and again I can just run that in the background to generate data more quickly. So these are all Raft elections. These down here were pretty decent elections. They're randomized, so some are better than others, but they're pretty good. This one seems like it took an extra term. It had a split vote that was resolved in the next term. And you know, this is still very slow because it's a JavaScript-based interpreter right now, but we can start to get a sense for at least under these assumptions, our election times seem to be typically decent, and occasionally we have these little spikes. And if we're worried about what these look like, again, we can click on them, scrolls the timeline to the right place, and we can watch this election. I'll slow it down a little bit. So what went wrong here? We have timeouts that are looking very similar on all the servers. It's pretty likely we'll get a split vote then. Wow, that's boring. I'm speeding it up. One, two, three, 4 timed out. So that didn't work. Just gonna try again. That time it worked. Okay. So that's what I've got so far. I'm hoping that other people will produce more models and that we can start exchanging those on GitHub. Back to slides. So, as I mentioned with Raft, like I didn't have a tool like this, and so kind of the best thing I could do was take existing tools and write system models of Raft in many different ways. So TLA plus as for the specification, about 500 lines. Raft scope, the visualization in JavaScript, about 300 lines. A simulator for leader election in Rust, about 550 lines. And pseudocode for the purpose of documentation, 150 lines. That feels a little too compact to me, so it's probably just not correct or skip some parts, but I'd never know because it's pseudocode. So basically you have to write these similar models for all these different systems, and then if you change your mind on the design, you have to go back and adjust them all. But with Runway, hopefully we can reuse the same model, and so that lowers the cost of doing this, and maybe we'll do that sooner. And also, because we're looking at the same model code from these different angles of simulation and model checking, we're more likely to find bugs in the model itself. Like, does that pseudocode have bugs? I'd bet money on it. Did my TLA spec have bugs? Yeah. Does it now? Hope not. And the other thing we get from integrating all this into one tool is that these things benefit from the visualization. So as you're writing a spec, if you can see it visually, you can you can watch your spec execute and you'll catch bugs. It's like a great debugger. The simulation, you saw how we can jump into data points and watch that visualization, and the model checking is similar. If we have an error, we can visually see how we got there. Okay, so the last section of my talk is on building the Runway model. So there's kind of 2 parts to it, as I mentioned before. There's the specification and the view. And the specification is describing these are the states that my system has, and this is how they transition. The view is less interesting. It's just saying this is how to show my state on the screen. So like, you shouldn't be thinking very hard about the view. If the view does its job, you probably don't need to look at it. that stuff's just built on some off-the-shelf components like JavaScript, D3, and SVG. The specification is definitely interesting, and it's where you are probably going to spend your time. I mean, the view can be tedious, but I guess the spec will be where you'll spend your mental energy. So how do you produce these things? I would like to start with sketching a view by hand. It's just like, it's way easier to draw on a whiteboard or to draw on graph paper than it is to draw in JavaScript. And then when you've got that view of, it's your mental model basically on a sheet of paper of how you think about your system, that's going to lead you to representing the core pieces of state, whatever you would need to update that programmatically. And so from that, you can define your types, define your state variables, and then I'd say go ahead and create your view based on those types and try to model it after your sketch. And the reason why you want that view so early is it helps with debugging. So as you're writing transition rules, it's really nice to just watch your state go through the transitions and make sure that it looks correct. Then you probably want to write some invariants. These are properties on your state that should always be true, like I have up to 8 bananas, and the system will let you know if they're ever false, so that can help catch bugs early. And then write transition rules, and these can start off completely unrealistic, like we're going to jump from I timed out to I'm a leader without any of the stuff in the middle, and then you can go and refine them as you go. Another tip here is while you're working on the view, or if you're working on transition rules, just set your starting state to something convenient. Like in Raft, about half the time you want your starting state to be I have a leader already, so that you don't have to go through an election process. So what does the specification language look like? Well, it's code, as I said, but it's not normal code. It's encoding what's called a labeled transition system. It's pretty much a state machine. So you want to define your starting state. Your transition rules say how that state may change, and invariants are properties that are supposed to hold on your state. And you use these rules to encode both expected behavior in your model as well as failures that might happen. So, the Raft model has a rule for drop a message, duplicate a message, shut down a server, that kind of thing. So the rules get applied one at a time, so they happen at an instant point in time atomically. You don't have to worry about mutexes or any of that stuff. You can model mutexes, but you don't want them in your model, in your modeling language anyway. And then, not every rule will apply all the time. Like I can't drop a message if I don't have a message. So you just encode that with an if statement in your rule, and if your rule changes none of the state, then it's inactive, and if it would change some state, then it's active. If multiple rules are active, then the simulator picks one randomly, and the model checker explores all paths. So here's, I've got the too many bananas code on 2 slides. This is the correct version of the code with a note present. So this slide's got all the types and variable declarations. It's probably not too surprising to people, but so all the types have a size. So the banana is some integer between 0 and 100. Whether a note is present is a Boolean, and then a person can either be happy, hungry, going to the store, or coming back from the store. If they're returning from the store, then they can carry some number of bananas, and the compiler will ensure that you can't access that field unless you are returning from the store. So I've got 5 of these person objects in an array indexed 1 through 5 called roommates. And up here's my invariant that I should have no more than 8 bananas. Okay, so here there's only one rule set for this model, and it's, let's one person advances forward. So this says for each of the roommates, we're just calling them state. If they are happy, then they can go hungry. If they're hungry and there's no bananas at home and there's a note present, then they can't actually do anything, so they just do nothing, and they fall all the way out of this. Nothing happens, and that rule is inactivated. But if there is no note present, then they can go to the store and pin a note to the front of the house. If they were hungry and there were bananas, then they can eat one and become happy. If they were going to the store, they can come back from the store, and that's where I generate the random number of bananas to bring home. And if they're coming back from the store, they add however many they were carrying to the bananas at home, they remove the note, and they return to the hungry state. And so you notice how this permits the interleaving where I came back from the store, I went hungry, but meanwhile my roommates ate all my bananas. And that's the kind of thing that you may want to consider when you're talking about distributed and concurrent systems. That may not be obvious if you were writing the code in a different style. So this is basically a template that's defining five rules in this case, because we have 5 roommates, and the simulator would randomly select between them, whereas the model checker would try all possibilities. Yeah, sorry, I can't even hear.
So, like the way I read this, the match state case where the person is happy, it means he will always be hungry immediately, or does that like get randomly applied?
No, it's more of
possibility.
If someone is happy, then they can go hungry.
Right.
But if other things could happen, then it's up to Runway to decide what happens next.
And the selection of the roommate to execute a rule on at any given time is random, or
in the simulator, yes.
Okay, thanks.
Okay, and the last issue I want to mention real quick. So, as distributed systems developers, like we like to think that there's this global notion of time somewhere that is like, we don't know where it is, but it's kind of at the root of the NTP tree. Physicists will laugh at you. They will talk their heads off about how this is wrong and how Einstein and relativity and there is no real notion of time, and who cares? Really, there's sometimes we care about time and sometimes we don't. Like in Raft, Raft should maintain safety. That is, it shouldn't eat your data, even if clocks misbehave. But then to talk about performance and availability, we really do need time because, how many operations per second can you do? Really, that per second has to be meaningful. And so Runway's current approach, and I don't know if this is going to work forever, but it's kind of worked so far for the few models I've done, is that there's this so there is a global clock. You don't get to access it directly. You go through this magical past function. And so this says, this is the rule in Raft to start a new election that says, are we currently past this timeout time? And if you're running a simulation, then it does the obvious thing of comparing that time with a global clock. But if you're running a model checker, or if you're running if you're just poking at this thing interactively, that just returns true, which is like it is always possible to time out in those environments. It doesn't really matter how much time has passed since you went to sleep. I don't know if anyone has thoughts on whether that generalizes, then I'd be happy to chat about it. But gonna keep pushing with it until it breaks. Okay, so to summarize, I think we should apply tools to help design distributed systems, and I think they're expensive to build, they're hard to get right. We should really be studying them and making an educated guess at this. And the way to do that, I think, is through modeling, which helps focus our attention on concepts and leave out unimportant details. So I think if we're talking about the design of a distributed system, it's usually a lot of stuff we don't care about, like processing time on a server is usually not very important. I don't know, sometimes network topology just doesn't matter. Whether the exact concurrency implementations inside a server may not matter. But there's stuff that really does matter, like the messages we send around and whether we can handle failures. So Runway combines specification, model checking, simulation, and visualization into one tool. And the hope there is that by combining it into a single tool and making that accessible and kind of fun to play with, that we could start using it more broadly, both in academia for teaching and learning, and in industry for communicating about our designs to others. So you can go check out the models, go build your own, and really it'd be awesome if anyone wanted to work on Runway with me. There's all sorts of problems there, from front-end work to compilers to crazy model checking optimizations that I don't really need to get into, but just a lot to do. In short, let's solve design problems in the design phase. Thank you.
Thanks, Diego. Some very interesting models on display there. Is there any questions from the room?
Yeah, right. So the question was, does the randomized simulation, is it seeded? Is it doing the same random thing as before? So right now it's not, and every time you go to runway.system or reload the page, it's going to do something completely different. I didn't know what would happen in the demos. You can do one thing, which right now, which is if you go look at the execution, you can download it, and then you get this huge JSON blob, and you can upload it back in later. It would be a good idea to do what you're describing, of basically let's seed the random number generator so that if we fix something in the model, maybe we can see what happens. But I guess what you could do today is you can download the execution, slice out the tail end of it, and just replay up to where you had the problem and go from there.
Any other questions?
For the model checker, have you looked at things like quick check and so on?
Quick check?
Yep.
So the model checker here right now is basically a stub, a placeholder. I'm familiar with quick check a little bit from Haskell. I'm not sure it's the same thing. So there are definitely existing model checkers, and it might be wise to compile down to one of those. We can talk a bit more offline, but I think quick check's just doing generating randomized data to try to explore different paths in your program, and that's not too far from what the randomized simulator does. But for model checking, I really want to be certain that I'm enumerating all paths. So what the placeholder does, what the existing model checker does, is takes the state, hashes it, puts that in a giant hash table, and then for every possible rule that it can fire, it will queue those up and explore those and hash the state. And if it won't revisit a state, but it's trying to get to every possible state and evaluating the invariance, and also looking to see if you reached a deadlock state. So it's kind of it's a different form of exploration than quick check, I think.
Thanks, Diego. Any more? Heidi.
Are you able to model node failures, and with the state specification, can you differentiate between volatile and non-volatile state?
What's a volatile and a non-volatile state?
As in the Raft example, can you say the commit index will be stored on disk, so if a failure happens, don't scrub that, but something else is only in memory, so if their failure happens, that's okay.
Okay. Yeah, so I mean, you're encoding the failures as rules, and there's no access control that's enforced by the compiler. So in a distributed system, your normal rules probably should only be accessing the local server state, right? But like I have in this reset stable leader thing where we run an election and then it waits for the cluster to be stable, like that's actually a pretty hard condition. It's waiting until not only is one server leader, but every other server has to be either down or agree that that server is leader, and there has to be a quorum of nodes up. So you can build in these pretty complicated conditions and just make that a function and throw that into your rule. And I've let's see, I've organized the so I've organized the Raft server state in this model to where the top part is persistent and the bottom part is volatile, and so when I shut down a server, it retains the top and loses the bottom. But did that answer it?
Yeah, that does. That was exactly what I was wanting to see,
Okay.
the kind of splitting of state.
Yeah,
like
and you could make those separate records to be a little cleaner about it, but...
Thank you. It's 4:25, so Diego, thanks for joining us. And there's a coffee break now, so feel free to make use of the food and drink outside.